The relationship between the standardized deviations of y and x and the correlation coefficient r is fascinating. We have two key equations that illustrate this. The first equation shows how the deviation of y from its mean relates to the deviation of x, scaled by the correlation coefficient and the standard deviations of both variables. It's like a dance between y and x, where the rhythm is determined by their correlation. Now, flip it around. The second equation does the same for x in terms of y. Here, the slope is also influenced by r, but it's adjusted by the standard deviations in the opposite direction. This means that the steeper the slope, the stronger the correlation, provided the standard deviations remain constant. These equations reveal how changes in one variable impact the other, giving us a clear picture of their interdependence. Understanding these relationships is crucial for interpreting regression analysis and making informed predictions. Welcome back to Chandra Shekher, Research Academy of Business Studies. In this video, we're diving into how to understand the regression equations and correlation coefficient, denoted by R, through some clear and practical examples. Today, we'll be exploring the relationships in regression lines for y on x and x on y, and interpreting what each part means. Plus, we'll look at some example problems to make it all concrete. To start, let's quickly recap what we mean by regression and correlation. Regression helps us understand the relationship between two variables, like how a person's study hours, x, might affect their test score, y. Here, our goal is to find a line that best fits the data points for these variables. We'll break down the equations for regression and explain how to use the correlation coefficient, or R, to interpret how closely these two variables move together. Let's go through the two main relationships we'll use. Imagine you have a data set of students' study hours and their corresponding test scores. We start with the equation that connects these values for y on x, which says the difference between each y value and the average of y is equal to the correlation coefficient, R, multiplied by the ratio of the standard deviation of y to the standard deviation of x, then further multiplied by the difference between each x value and the average of x. In other words, we can estimate how much y changes when x changes, and the correlation coefficient R tells us how strong that relationship is. For instance, if R is high and positive, more study hours tend to increase test scores. This equation reverses the relationship, letting us understand x in terms of y. It says, the difference between each x value and the average of x is equal to the correlation coefficient, R, multiplied by the ratio of the standard deviation of x to the standard deviation of y, then further multiplied by the difference between each y value and the average of y. This equation is useful when we're predicting one variable, like study hours, based on another, like test scores. Let's look at our first example problem to make this clear. Imagine we're tracking study hours, x, and test scores, y, for 5 students. We'll compute the correlation coefficient, R, using their data, which shows a moderate positive relationship of R equal to 0.65. The mean, average study hours, or average of x, is 5 hours, and the average test score, or average of y, is 70. The standard deviation of study hours is 2 hours, and the standard deviation of test scores is 8 points. Now, let's say a student studied for 6 hours. Using the equation for y on x, we can predict the test score for this student. First, calculate the slope, the correlation coefficient, 0.65, multiplied by the ratio of the standard deviation of y, which is 8, over the standard deviation of x, which is 2. That gives us a slope of 2.6. Next, apply this slope in the equation by taking the difference between the study hours, 6, and the average study hours, 5, which gives 1. Multiply this by the slope, 2.6, to find the expected increase in test score, which is 2.6 points. Adding this to the average test score of 70, we predict that the student will score around 72.6 points if they study for 6 hours. For our next example, let's reverse the question. Say we know a student's test score and we want to estimate their study hours. For this, we use the regression of x on y. Using the same data, the correlation coefficient remains at 0.65. This time, our slope is found by multiplying r 0.65 by the ratio of the standard deviation of x 2 over the standard deviation of y 8, giving us a slope of 0.1625. If a student scored 75 on their test, we can calculate their expected study hours. First, find the difference between the test score, 75, and the average test score, 70, which is 5. Multiply this by the slope, 0.625, to find the expected increase in study hours, which is 0.8125 hours. Add this to the average study hours, 5, predicting the student studied about 5.8 hours to achieve a score of 75. To recap, when we use regression analysis, the equation for y on x gives us the predicted y value or test score based on x or study hours. The equation for x on y allows us to predict study hours if we know a test score. The correlation coefficient r is essential in each calculation, as it tells us the strength of the relationship between the two variables. By understanding these formulas and applying them to real-life examples, we can better understand how regression works and predict outcomes more accurately. The key takeaway is that a high correlation coefficient, whether positive or negative, results in a stronger prediction, while a lower correlation means our predictions might be less reliable. Thank you for watching this video on regression analysis and correlation. If you have any questions or want to see more example problems, leave a comment below. Don't forget to like and subscribe to Chandra Shekher Research Academy of Business Studies for more insightful content like this. See you in the next video.